Yeah, thanks a lot, Eric, for inviting me here for a kind of introduction, although I'm still a reader, not a professor, but that's fine. So I will talk about approximating transport maps, and one can think of those as just a change of variables if you have never heard of those. And it turns out that it's kind of state of the art in computational statistics nowadays. And pretty much all of this hype of AI with generative models is actually a transport map at the end of the day, just implemented by a complicated neural network. But it turns out that for more classical problems, you can actually use more classical methods as well, like the tensor trains, or you can even use polynomial chaos if you like. But the funny thing is that you can actually make it deep, so you can connect it into deep layers like neural network. But that becomes more informative now. You can improve some convergence theorems. That's quite interesting. And one thing, what I will present in the end of my talk today is how to apply this to simulating rare events. So the thing where we may know if the event is rare, the probability of hitting it by chance is extremely small. So we need to somehow bias our function where we sample towards that set. But how do you find the set which is not even easy to find in the first case by chance? So that's exactly also where we want to make a deep approach of this. So we want to make a nested set of functions which would gradually approach that set of interest, the set of rare events. So what statistical inverse problems? Basically, we can think of this configuration here, like often appears in classical inverse problems. We assume that we have some parameter x. That's basically what we want to find. And that can be something like the distribution of permeability in the soil, where it could be water, where it can be sand. They have different densities, different thicknesses. Basically, this will allow parameters. So potentially our parameter can in fact be a function in some Hilbert space. So it could be infinite dimensional. But of course, in practice, we often discretize it. So in principle, we can think of X as a vector in practical computations. But of course, because it often starts from infinite dimensional function, this vector is still large. And that's where we'll get this curse of dimensionality. So the parameter we want to infer is high dimensional. Then we have some model, and that model could be, for example, diffusion convection, like basically where we have this distribution of the contaminant. Then we can simulate the diffusion, advection, maybe reaction as well. And what this gives us, basically, it gives us a prediction of something we can measure. On the left, y is the measurement. And the measurement could be, for example, this concentration of this of the smoke or something like this. So then we can measure how much of this contaminant has actually leaked on the boundary. So we have some forward model which predicts the exact measurement of this parameter. And this model is often nonlinear. It's at least once differentiable, but otherwise it can be pretty complicated. And then we also always will have a noise. So again, it's slightly more difficult problem than classical inverse problems because this noise is intrinsically there. And not necessarily we can just regularize it. We really want to think of this problem in the stochastic way. And there is a way to do this. The very classical way is the Bayesian formulation. So we are looking at Bayesian inverse problems. And basically we say that for our parameter x, we need to have some prior knowledge. And if we have no better idea, it could be just Gaussian, just independent Gaussian parameter. And that would correspond to the Tikhonov regularization in the classical inverse problems. But if you have no better ideas, we could even use uniform priors, and that's used a lot when we have no idea. But if you do have some knowledge about the prior, like we know in which regime we are working, we can make something more informative, and this will give us high regularization. And then we have the likelihood for the data. So if you observe the data y here, we need to have some likelihood, which is typically just the probability density function of our noise variable. And like, for example, if the noise is standard Gaussian, like here, then we just need to compute the residual between the data and the model. It can be weighted with this covariance of the noise. then essentially we take the squared residual gain and take the exponential of this, which is not normalized, but the likelihood doesn't have to be, because then the product of the two by the Bayes theorem is proportional to the posterior. So if you normalize this, we'll get the actual posterior density. But the good thing is that the methods you want to consider should work without the normalizing constant, ideally. So either they should compute the normalizing constant explicitly if they need to, and that's exactly what will happen in rare event estimation. But if you just want to simulate the posterior, then basically these two functions, these two formulas are all we need. And the MCMC can do this, but transport map, as we'll see, can do that as well without normalization. Right, and then why we need this? Well, basically what we want to compute in the very end is probably just the expectation. So we have some another function, which is quantity of interest, which could be something like the total amount of contamination, or actually the probability could be that the ground contains oil, for example, some subsurface event, or it could be the probability that the waste will leak in like 10,000 years, and that's what we want to estimate. And we just need to compute this integral with the posterior. And if we could compute this integral analytically, the problem would be solved instantaneously. The problem is, of course, we can't compute this analytically because this is a complicated function. And it's tough to compute numerically too, because usually this distribution is not analytically sampleable, so we cannot just generate independent random numbers from pi directly. So then we need to do some approximations. We probably still want to use some sort of Monte Carlo or maybe some other quadrature, but we need somehow to make it distributed according to this pi. And that's difficult because it's high dimensional, so how we even characterize it? And even worse, it can be concentrated. And actually, that's a problem that in particularly interesting scenario when the noise is small. So when our data is actually accurate, numerically, this is the hardest problem, because it may well happen that this function is concentrated, and if this function is concentrated in high dimensions, it's difficult to even find where it's located if it's a very thin subvolume of a high dimensional space. Like some of the very thin tails here, it's really difficult to find. In principle, the ultimate method is kind of easy. We just do the Monte Carlo quadrature, but these points should be sampled from the approximate posterior, and how to get one is an interesting question. So traditionally, people used just Markov chain Monte Carlo for this, or more specifically in the classical method, it's a random walk MCMC, where what we do literally, we sit at some point and we make a literally random move. For example, by sampling a direction from the normal distribution, and we make a move. And well, then what MCMC does, we have accept reject, so we form metropolis ratio with the exact function, which doesn't have to be normalized. And then we can accept and reject, and under some mild conditions, we can prove that actually the samples which we generate converge to the correct distribution. But of course, if you have any experience with MCMC, you know that typically we have very long correlation times. When we have a large burn-in before we get anywhere in the vicinity of this distribution, then we have very long correlation times, because these samples are correlated because of this random walks. And the variance is large. If you just want to look at the quantity of interest, who cares about these correlations? Well, still the variance will be large, and this means that the error in the estimate will eventually be large. So transport maps potentially look like a bit of holy grail here, because they tend to distribute the samples somehow fairly. So basically, they tend to generate samples distributed directly according to the target density. And how they can be done? Well, as I said, basically with the change of variables. So we assume that we have some variable u, which we can generate directly with the standard random number generator. So u is a uniform random variable, or uncorrelated normal random variable. Super easy to generate in any programming language nowadays. And then we have another function, which is actually the transport map t, which is this multivariate function which maps into the value of x. And this x, if you make u random, then in a uniform cube, let's say this x will be here. Then, of course, we need to approximate this t now. So in some sense, we made the problem even more difficult. We wanted to approximate just one probability density function for the posterior. Now we need to approximate d-variate probability density function. So in some situations, the map is slightly easier than the posterior, but in general, we need to think how to do this. So basically, this is a more mathematical formulation of this. If you ever have experience with differential geometry, you can recognize the notations directly. If not, again, as I said, just think of t as a vector function from d variables. But then you can say that if you have this p, this reference density, like the standard normal here, you can make a push forward of this density with this map. And ideally, you want to make this exactly the posterior measure you want to compute, like, for example, this concentrated. And ideally, the map should be invertible. Of course, you should be able to generate x from u, but vice versa, you should be able to invert this map. If it's a nonlinear function, that's another question. But let's say you did this, then the Monte Carlo is easy. So you generate just this u from the standard normal, for example, very easy. Then you compute this function on all the samples of u point-wise, and then you average your point of interest. So if you manage to compute this transport map, basically all post-processing you can imagine in statistics and UQ is easy, just this. But the main goal is how to compute this transport map. And historically, there is kind of two paradigms to this, because the way it came from first is probably machine learning. And when we talk machine learning, we typically talk data. So we're given some data, and then we want to, well, basically learn. We want to compute some sort of function from this data. And the typical problem here is called density estimation. So we're given some samples from the exact posterior. So in some sense, you can already see that this problem is different from what I presented before. But in machine learning, this actually makes sense, because what happens in the left column here, we can have, for example, images of, well, whatever, cats, dogs, classical one, but we could have images of different species, whatever. And we assume that these images are samples from the distribution. So we assume by statistical learning theory that there is the ultimate distribution, the true distribution of cats, dogs, and mice, whatever. And whatever image we see is a sample from this. So given the samples, we want to actually compute the map t, compute the distribution, the map t. So we can form some empirical risk, as always in machine learning, which could be some distance between probability measures. And then we can optimize over some parameters in T, which are done typically in neural networks nowadays. And there's few methods which look like this. So one of the first was generative adversarial networks. But in fact, since then, there is plenty of methods which do the job. And in principle, we can use it for our neat engineering problem, if you like, inverse problems. If you want to simulate the leak of the contaminant, we can still use this approach, because often we can sample from the joint density, and then we can marginalize it. So there is a way to do this. But given these engineering problems, we can do much better, in fact, potentially, because we can do the density approximation instead. And the crucial difference is, as we saw in the Bayes theorem, we are given the precise expression, the precise function, just for normalized density. So we don't have the actual posterior, but we have the normalized posterior. And for this, we have the precise function. So potentially, we can make our approximation, our map, as accurate as possible. And this is crucial from the left-hand side, where we're giving fixed samples, and that's it. Here we can potentially introduce as many samples as we like. So we can use, we can naturally introduce active learning. And this is exactly where the tensor-train methods will actually kick in, because they had an active learning algorithm before it even became like a mainstream in neural networks. So that it's much easier to train a neural network with adaptive sampling now, rather than just minimizing some empirical risk on the given data, on fixed data. So then we will approximate actually the density. So instead of approximating the map, I kind of roll back and I want to approximate the density in a tensor-train. But the reason for this is, if my density will be in tensor-train, the map is the easiest part of the story. So you can get some of the best maps. I can hold this called autoregressive map, or just triangular map, which will be easy to differentiate, easy to invert, easy to compute Jacobian of pretty much whatever you can think of. And then if I have the map from this density, I can easily make a chain of them. I can make a deep map for some difficult approximate densities by making it recursively. And again, I don't want to just train a single map or like even a deep map as a neural network. really want to make it gradual with adaptive sampling along the way, because I can always put my hands on the truth of the function expression. So density approximation, if we have the classical inverse problems written in Bayesian formulation, we can do something much better by actually approximating the density. So I said, if you want to approximate a density, then the map is the easiest part of the story. So let's look at this. And the answer to this was actually done some 70 years ago, more than 70 years ago now, in one of the first papers on this applied probability by Rosenblatt. That was called this inverse Rosenblatt transport. So I assume that we have some unnormalized density. I will just call it pi for brevity, but think of it as a normalized posterior or something else. So the idea is actually very easy. So we need to compute marginals. And in the first step, we just compute the marginal in the first variable. So we need to integrate this density, which is normalized again, over all but the first variables. And then this is one-dimensional function. So we can sample from this one-dimensional probability density function. That's easy to do. We can use one-dimensional, we can compute one-dimensional cumulative density function numerically. We can invert it using the Newton method or using bisection, whatever we can do in one dimension. Everything is easy. But then we can just recur. So now this is the base of our recursion in the first coordinate. And if we assume that we have k-1 coordinates, then essentially we need to condition our full density or joint density on the previous k-1 coordinates, still marginalize it over the last d-k coordinates. And this gives us still this conditional density, but essentially the fixed samples we have already computed. It's a one-dimensional density, and we can again sample from this one-dimensional density. And the function which will look as a sample from this we'll call tk, so the kth component of our map. And there we go. So then we can finish up. So in the final step, we'll just sample from the full d-dimensional conditional. And we get this kind of best map of its kind. So we just need a density. We just need to be able to integrate the density. Then we automatically get the map. The map comes out triangular in the sense that each component depends only on the previous variables. So it's immediately invertible. So to invert it, we just need to deal with one variable at a time. And if we want to write the Jacobian, it will be triangular matrix, very easy to compute determinant of. Problem. This integration here is as difficult as the original normalizing constant. Perhaps even more difficult because now we need to still kind of sample x1 on a discretization grid or something like this, and still integrate over essentially d-1 dimensional space, which is almost as difficult as the original one. But this is exactly where I want to use the tensor-trains. So if I lower my ambition a bit, so I don't want to compute this Rosenblatt map from the exact density. If I'm happy to compute it just from the approximate density, which is done in the tensor-train, then I can get rid of these integration problems. In principle, that's exactly what functional tensor-train was designed for, the ease of computing integrals in high dimensions. So let's see how we can do this. So we need some class of models, which is easy to integrate. That's what we want. Now, for some reason, I want to approximate the square root of my pi. This will be clear in a bit, but I assume that you can find some function, some approximate function, which approximate the square root of my function. And sorry, neural networks. In this case, I really have to abandon them because neural networks are easy to evaluate, they're easy to differentiate, but they can't be integrated because of non-linearities in between. I can't integrate a neural network. So actually, if anyone will come up with an idea how to integrate a neural network fast enough without like retraining the antiderivative, that would be super awesome. But so far, I can't really do this. But basically, let's say if I have something to integrate, then I can square my approximate function. That would be approximate pi, but it will guarantee to be non-negative. So from this, if I can integrate my square of my approximate model, I can immediately get the map, and I'm guaranteed that I'm always integrating the negative function, so I can normalize it, and this will guarantee that I have a monotone and smooth map. So it's invertible, it's automatically invertible, and I can even prove a theorem that the Hellinger distance between my actual distribution and the push-forward with my approximate map is bounded by the L2 error in my approximate square root. And you can imagine that L2 error is a nice thing to optimize. So if you want to optimize something, then quadratic loss function, the quadratic objective function is always easier than something else we can imagine. So we are dealing with nice quadratic optimization if you want to optimize. But as I said, for TT we can do something slightly different. So we have this error bound immediately on the distributions. That's good to have. So now I really rolling back. So I said, okay, I want a class that is easy to integrate, and perhaps the most stupid one and the most easy one is just the linear ansatz. So I have some basis functions phi j, and I just want to decompose my tilde j, this function, with some coefficients in front of phi j. Obviously, it's easy to integrate. I just integrate my basis functions, and of course, if I know basis functions, they should be easy to integrate, and sum them up with coefficients, and we are done. The problem is, of course, the cursor dimensionality. That's exactly what I wanted to avoid. If I have no better idea, then this phi and the number of these basis functions needs to be exponential in my dimension. So let's decompose it. So let's now do the brain decomposition. So firstly, as I said, if I work specifically in UQ or computational stats, typically I work in a domain which is easy. It could be the full space, or it could be a hypercube. And basically the idea there is that I can introduce my basis with independent indices. So I can, for example, I can introduce just univariate basis functions. So in each of the variables, I can introduce some basis function, and I can just multiply them together. And obviously, I get my coefficients numbered by several indices, which just come from this one-dimensional basis indices. And this is my ansatz. It's still linear in the coefficients, but my basis function is decomposable. So the way to introduce this, I need to have some sort of like independent ranges in the variables, for example, the full space. But now if I have this index decomposition in the coefficients, I can decompose the coefficient itself. So now, because this coefficient has multiple indices, it's not just a vector, it's a tensor. So it's an array of many indices. But now I can try to factorize it as well, like write it as a sum of products of these just univariate factors. So each of these new factors has only one index j at a time. Then I can swap the sums, and basically I'm getting this, which is like a functional tensor decomposition. So now each of these big brackets here is a univariate function. And of course it has some coefficients, but otherwise it's just really separation of variables. And we can imagine that it's probably easy enough to integrate it, because still we integrate just one-dimensional functions. So we can pre-integrate this phi, this small phi, the one-dimensional functions, and we can even sum up this integrated phi's with the j's. So we just need to sum up over a single index j. But then we can multiply these brackets. We only need to sum of this auxiliary index s. So this S is exactly what distinguishes different tensor decompositions. So we can imagine that, okay, we can probably just literally sum over a single entry of S, but this is probably not the best scenario. So we can think of S actually being a vector of summation indices, and we can make more interesting structures within the separation here. So what we can try to do? Well, we can try to start with simple matrix decompositions, because we know that a similar separation variable exists if you want to factorize a matrix in the factors of rows and columns. And that's what we can do. So we can group all but one index together, and then basically look at this tensor as a matrix. We can decompose these two factors. And obviously, this is just a matrix decomposition with one extra summation index here. But then I can do the same procedure with this remaining high-dimensional factor. And the take here is I want to group this S1 and J2. So I want to separate these two indices out of the rest. So here I have d-2 index. But this summation here contains only one auxiliary variable S2. And I can use the matrix decomposition for this. And you can recall that if I want to just decompose the matrix, I can probably use the single value decomposition, which has a guaranteed Eckert-Young optimality result, the optimal convergence in this rank introduced here. And then we can already see that I introduce more than one rank. And then I can continue recursively until I get my one-dimensional block. And that's basically what was coined as a tensor-train. Because I have a tensor, I want to decompose a tensor, but the model of my decomposition, approximation more generally, looks like a train, because this auxiliary summation index couples only two factors at a time. Otherwise, the factor is one-dimensional in the original index. We have this coupling thing. And the reason why it was quite useful why it was introduced, because it shares this recursive matrix factorization. So it has, for example, closedness. If you fix the rank, that the set of matrices of fixed rank is closed, the set of tensors of fixed rank is closed. Then we can approximate. But now we can also introduce functional tensor trains. We just need to plug in these basis functions, sum them with these new coefficients, and then basically we get this separation of variables, but with this train-like summation structure. So again, it's easy to integrate. We can integrate these univariate functions and we sum them up recursively, and then we get our integral on the left. But also we can notice now that if you want to do the Rosenblatt transport specifically, that's also pretty easy because we can integrate over subset of variables. We don't have to integrate over all x1 to d. We can integrate, for example, over this x3 to xd only, and this would be a one-dimensional operation. And in x1 and x2, we can take a conditional, and again, this would be a one-dimensional interpolation. So any step in the Rosenblatt transport is very easy in this format. And that's why I said it's the easiest part of the story to get them up. If you get a density or square root of the density approximated this way, it's very, very easy to do the one-dimensional numerical integrations and get essentially the exact map from this approximate density. And it's also very convenient to compute these approximations. So if you want to get these coefficients in the tensor train, basically this is where the TT-cross algorithm comes. So like, now we can call it active learning because we want it samples the function adaptively. So it starts from some initial guess that could be random samples if we have no better idea, but we can possibly have some prior samples. And basically all we need to do in each step, we assume that we are in recursive steps. So we have k-1 components pre-sampled and the d-k components pre-sampled. Then we just need to compute the TT core, which is exactly the function we want to approximate. It's square root of pi, remember, on these samples. So this single variable is sampled in full, but the other variables are subsampled. So we assume that we have some initial guess first, but now we can actually adapt them because as long as we have this small factor, this is single TT core, it's a low-dimensional object. We can do the pivoting operation on this, and if we have no better idea, we can just use daily decomposition of these coefficients. If we reshape them in the matrix, we can use daily decomposition, or we can use the volume maximizations, more advanced algorithms, or we can use DIAM if you like model reduction to get new indices in this xk, in this new variable here. So this sets up the recursion. So we had k-1 and now we have xk. So we can move this active variable to k+1 now, because now we have this green indices for one more variable. In this way, we can iterate really back and forth. So we can iterate over this chain of tensor cores, over this train. By the number of samples, we can immediately imagine that we have the number of samples from function which is linear in the dimension, quadratic in this rank, this happens, plus some other linear algebra operations in this pivoting, which is also linear in the complexity. So in this given xk, in this one variable at a time, we learn everything possible. After the discretization, of course, but this discretization can be made very fine. Because we only need to discretize one variable at a time, we can introduce whatever polynomial, Chebyshev polynomial degree 100, if you like, and there is not particularly onerous. So we can really literally say that we learn pretty much everything about the function in that variable. And then because we do this pivoting here, we adapt the next samples for faster conversions. And how fast? Well, in practice, actually, you should aim at something like 10 iterations max. Because in principle, you can imagine that probably not all functions can be approximated in this format. We can imagine, for example, discontinuous function going along the diagonal, where we don't really have a chance well, if you look at basically something like a triangular matrix, it's obviously full rank, so why would you have this low rank position? So if we have a lot of iterations of this algorithm, this probably means that we have a function which is not exactly good for this approximation to begin with. And for everything like weakly correlated probability density function, we should typically have a very fast convergence and very fast adaptation of samples to the optimal positions. So again, this is all possible because we are solving the Bayesian inverse problems where we have the density approximation. We have the formula for the normalized density or the square root thereof, so we can evaluate it anywhere. But then we can do this adaptive sampling and compute it quite rapidly. So briefly, what I already mentioned. So what functions are good for this tensor-train approximation, what are not good? So there are theorems. For example, that the smooth functions, meaning the mixed Sobolev attribution, if the function is a mixed Sobolev space, then one can prove that actually this function exhibits fast convergence of the tensor train, and this is connected to the fast convergence of polynomial chaos. But also there is a separate theorem for computational starts if the function has local correlation of variables, so only like neighboring variables are strongly correlated, but the covariance matrix, for example, in the case of the diagonal, then we can also prove a fast convergence of the tensor-train approximation. But in contrast, if we have a non-smooth function like discontinuous function, a function which we know that there is strong correlation of the first and last variable, for example, then we can see both in theory and practice that the convergence may be slow, so we need high TT ranks, and that's, of course, not very efficient. So what about concentrated density functions? So we do want to approximate concentrated functions because, again, this is exactly the scenario where we have accurate data. When we have informative data, our likelihood is concentrated, so posterior will be concentrated. And same will happen for Bayesian of rare events. Again, the rare event will probably have a concentrated indicator function. So we want to deal something with this. So somehow we want to apply TT to this right case, where it doesn't seem to be immediately applicable. But now we can use the TT to build the transport map, but we can also use the transport map to help TT approximate functions of this kind. So the curse of concentration, how we can call it now. So if pi is very complicated, and basically, even before talking about rare events, we can just talk about these two bananas, which probably not a big deal in 2 dimensions. But if you imagine these two bananas in 100 dimensions, then how would we even detect them? Because the volume of each of these bananas would be like something like half to the minus to the 100, and that's a very small number. Or we can definitely expect probably have a huge TT ranks if we approximate it directly. So that's where we can approach this problem gradually. And the least intrusive way is to probably temper the density. So if you have the density, you can just raise it to the power less than 1. We have a formula for the density. We can always do this. But for this particular function, for example, if you do this, we can imagine what happens. If beta is exactly 0, this will be just 1. It's a constant. So if beta is much less than 1, we will probably have some function which is, well, somehow close to constant, or at least maybe it will look like a pretty isotropic function. And like, for example, this function looks like this. Yes, it's the first layer, the very rough layer of this function, the overall distribution of probabilities, so it's small and gated kind of this way than the other way. But this is easy. This is exactly the function where you can expect the TT cross to converge in like a handful of iterations, maybe like even a couple of iterations, really. Very isotropic function with low TT ranks, very smooth. So also the discretization will converge fast. But now we can think, okay, well, if you can approximate this tempered density, now we have a mechanism, we have the Rosenblatt transport to generate a map. Yeah, so out of this any variable u, we can compute t of u, and this kind of is distributed according to the pi, or approximately at least. So now instead of using random points in this reference variable u, we can use another grid. Because if we have a map function, we can think of it as just a change of coordinate, not that as transport map in all the sense, but just as a change of coordinate. So we introduce just the Cartesian grid, like the uniform grid in U, and then this map will make us some curvilinear mesh in this X. Okay, so we can use it as a mesh generator, probably, but why would we use the mesh generator? Why would it be useful? Because also we can notice that if you just vary this tempering power a little, the functions cannot probably change much. They will probably reveal finer and finer structure, but as long as this beta varies gradually, it will be revealed gradually. Again, so the functions with close tempering parameters will probably be similar. And now we can do the trick. So we can evaluate the function next tempering parameter at the mesh generated from the previous parameter. But this mesh was already kind of it was mapping in the distribution of the previous function. So if we compute pi beta on its own map, it will probably be just isotropic function because we have already moved the distribution into this pi, whatever it looks like, pi beta. So if you compute the same function on it, it will probably factorize into independent functions, factorize into marginal probability density functions. Now, then, of course, if you write this beta, this will never be exactly factorizable, but probably it's a good candidate to approximate by the tensor-train. And that makes the dirt. It's deep inverse Rosenblatt transport. So when we build this T from the Rosenblatt transport, but we make it deep because if we can do it twice, we can do it as many times as we want. So we introduce some bridging densities. And if you have no better idea, we can just raise the original density to the power. So we can just use the temporary. And all we need to do is the last power is 1. So in the end of the day, we need to get the original pi. And then in each step, we approximate the ratio of the two. So basically, in the first step, we approximate pi 0, which is like the most temperate function, as we just saw. But then we approximate the ratio of the two on the current map I built up. So why it's a ratio? Well, actually, because the Jacobian of this map is approximately pi L. So that's just the differential geometry. In principle, we can even use divide pi L plus 1 by the exact Jacobian of this, but there can be numerical errors that creep in. So it's easy to just compute this. And of course, for tempering, just the difference of these betas in the denominator, in the power, it's easy enough. And from this, I can approximate now this ratio in TT, and I can draw my new Rosenblatt map, which is just a surplus map. It's not the immediate map, just the current level. And then I can nest them. So I can take the previous map I built so far, and I can compose it with this surplus map, and eventually I get this deep network. Well, we can kind of call it network, but in fact, each layer now is not an obscure sigmoid function like a neural network or anything, or ReLU. But each layer is Rosenblatt transport driven by some bridging density. So we know what is a bridging density. We can think, okay, it's a tempering, so it probably recovers a particular scale of the model. Or like what we will do for the rare event, it's tightening of the area of the subdomain where the event actually lives. And then we can think of like more and more confident resolution of this event. So we know what these things are. And also they computed gradually. So we don't need to train them all with the stochastic gradient descent. We can use the t-cross for one of them at a time. We can always check the error. And we can see if the error is too large. We can probably recompute just one map to make it more accurate. We can increase this TT ranks to make it more accurate. Or we can even roll back a little if you want, but we don't need to erase everything or like optimize everything from scratch. So if you compose the map by this condition here, so the final, the bridge density is the exact density. So the push forward with this map eventually will be approximate density. So that's what we can use. That's we can use as a proposal in MCMC, that we can use as important sampling. We can use QMC, Quasimodo, for example, in important sampling regime. Many ways how we can do. So for the two bananas functions, that looks very particular. So these are the bridging densities, and they're just temperings, right? So you can see that really the bananas start separating as we get beta towards 1, but firstly they look like a unimodal function actually. And in each step, you have a low rank function. So this is low rank, and then we can map from this normal function to this one, and compute the ratio on this zeroth map. This is how it looks like. So it starts getting some multimodality now, but it's still very isotropic, and it never goes to like very small values. So if I run the t-cross, basically wherever I put my initial guess, my random points here and here, they will get into some areas of significant probability. I can learn something. And then I compute the next map from this, and I can compute the next ratio in the composition of the map. And look at this, although the bananas separate in the original space, in the transformed space, we do get multimodality, but the functions start looking pretty much the same. So we get this heart shape, but the device, it doesn't like spread apart. It doesn't concentrate. And that's what allows us to compute a rapidly convergent TT approximation on each of these functions. Never mind this one, which is probably impossible. There will be a lot of loose ends, but this one is pretty easy. This is a nice technique, and yeah, so what we can see that it can even rival neural networks, as we can see in the numerical results. So this, like this one, very simple model, but It's actually a bit low-dimensional model, but it can already uh, show that neural networks are surprisingly ineffective here, actually. Just this AR model, and we want to calibrate this infection recovery rate from a small number of data points. So the data is not sufficient to recover the parameters everywhere, depending where the data is. And in fact, we approximate just a six-dimensional function here because basically we want to approximate the joint density, and then we want to conditional it on the data. And this allows us to sample from this. And this is what hierarchical invertible neural networks, for example, can do. We can generate samples from the joint distribution, and we can train a neural network to map from the reference to this joint. But this particular invertible neural network can be conditioned on data. So if you condition the joint density on the data variable, you get the posterior in your parameter variables. And here we measure the Kellinger distance between the exact density and the pushforward with our map. And then we basically with the logarithm of the Kellinger distance, so the lower the better. And we can see that this neural network, which is quite sophisticated, it took, I think, like something like 8 layers of 400 neurons in each, half an hour of GPU training. But still, the Kellinger distance starts from basically 1 over square root of 10 at least. So then for some data points, actually, it can be as large as 1, the Kellinger distance, which means basically the neural network doesn't approximate there at all. Well, same can happen with any approximation method. Potentially, if the data is really off the training set, then probably there is nothing we can hope for. But still, this deep Rosenblatt transport driven by DT can get much more accurate prediction on majority of data. So there is a little outliers, but for vast majority of data, we get systematically more accurate approximation of the posterior. Even qualitatively, so what we can look at few examples of data, so few data points. And basically this one, for example, is where the exact posterior gets bimodal, it's get multimodal, but the neural network can only capture the dominant mode, but doesn't capture the next one. Actually, if this one is more accurate, this one, the truth parameter will never figure this out. If the exact posterior is unimodal, it's fine. Both methods perform the same. But even if the distribution is unimodal but elongated, the neural network can miss all of this tail, which is of course not ideal, despite spending much more training time, much more computing time. And now talking about rare events, and to set up the scene first, to set up the benchmark problem. This is exactly that model of subsurface flows. So we have this Darcy flow, the Darcy model, pretty much classical one in UQ. And we have some log normal field. We can just simulate it with the Carhunian-Loeb expansion for simplicity. But then we want to put the tracer particles. We want to put a tracer particle on the left of the domain, and want to see how fast it gets on the right. So we want to check the breakthrough time that the tracer particle basically approaches the right boundary here. And of course, we have some flow field driven by this permeability times the gradient of u. And now we want a probability. So we want to set some threshold for this breakthrough time. And we want the probability that the actual breakthrough time, which is a random variable now, is less than this threshold. So it could look like this. For example, we have a true diffusivity, which has a channel here. And it really depends if you put a particle in the channel, so it can traverse very quickly through. If you put the particle off the channel, if you put a barrier here, then the breakthrough time may become much larger. And but we don't know this beforehand, of course, because this is a random field. We cannot measure it directly. So we want this probability. And we want to estimate it also in the posterior configuration. So we can measure the water table. So we can measure this u at some points and this grid of points. And from this, we want to infer probably the diffusivity, but that may not necessarily work well. So like, for example, this is discontinuous. The Carhunian-Loeb expansion gives us a smooth field, so it kind of reproduces the channel somewhere, but not ideally. But we want to estimate the probability. I mean, whatever is the estimation of the channel, actually, we want to estimate the probability of this breakthrough time. So how do you compute probabilities of events in general? Well, basically, yes. So we compute the probability of this thing, and then we need to integrate the indicator function with the density or which we want to compute this probability. So the independent function is kind of clear. And then we can, for example, compute the prior probability, which is just integrate with pi 0. And in some sense, it's easy, but only if this function is easy to approximate, which is probably not. And it's more difficult if you want to compute the posterior probability. In this case, we do need to compute the normalizing constant. So firstly, we need to compute the normalizing constant of the posterior, and then we compute this Bayesian function. So we multiply the normalized posterior with this indicator, and then we need to compute the ratio of these two integrals, and it will be exactly the probability. So in principle, we can approximate this optimal Bayesian density. So if we sample from this function, we just need once. If you sample exactly, we just need one sample to get this probability. But of course, we will approximate, and then we need to integrate. And the problem is, of course, if this tau star is small, so the event is rare, so you have a very fast particle, then of course this indicator becomes very concentrated in one corner of the domain, or worse even, if it's concentrated along some strange subdomain, which may be disconnected even potentially, who knows. This pi star can be quite difficult. And this indicator is also discontinuous, so that's the thing, but we said probably not good for TT. But this is exactly where we can replace this indicator by the smooth indicator, and like the obvious smooth indicator, the sigmoid, so it's even analytic. So you just make the sigmoid, and then we introduce the weight gamma here. And of course, if gamma is small, then this function looks, well, in the end of the day, it looks like a constant almost, but here we have some very smooth function. If gamma gets larger, we get close to the indicators, in the limit of gamma infinity, we can approximate it actually. And now we can apply this dirt, so we can also change this gamma gradually in these layers. So we can use this gamma as a parameter for this bridging densities. We can make the sigmoid, multiply it with the posterior, and this will become exactly well, the final density if you get a gamma. But if you make a beta, so if you decrease this gamma here and we also temper the normalized posterior, this will become a bridge density. So it's really this step, and you can imagine that if I vary by beta much less than 1, then my gamma will become in this regime. So whatever gamma I use in the end, it will get smaller, and I get my sigmoid function, which is easy to approximate, and I get my tempered posterior, which is easy to approximate. And as I go through layers, I gradually approach this situation, but now my transformation of coordinates will put my samples predominantly along this interface, and it will be still easy to resolve. So I don't need to approximate this interface in the full space where it's extremely difficult to find. In the first case, I will get my important sampling driven from these layers of Rosenblatt transport. So what we did, firstly, we compared them in the prior probability, because that's much easier actually. And we compared with the classical cross entropy. So in principle, the cross entropy is also a sequential important sampling, but it uses just the Gaussian as a model to approximate the density function. And we have this concentrated indicator function. This is not ideal, of course. So essentially, if you just look at the error, basically standard deviation of probability itself, and then we write the dimensions. Now the dimension goes above 20. Then the cross entropy basically stops. So here we couldn't even compute. I think this Gaussian mixture becomes ill-conditioned, so we couldn't even proceed here. And it needs a lot of points to reoptimize the covariance and the mean of these Gaussian mixtures and the weights as well. If you use the dirt, then essentially the error is about 1% independently of the dimension, and the complexity is linear in the dimension, because basically what I do here, well, I just keep the same number of layers, the same TT ranks, and it's only the number of TT cores which grows linearly in D, and that's exactly what I have in the multiplier of my complexity. And now if I look at the posterior estimation, so in this case, the cross entropy, we were unable to run. So it didn't give any meaningful result at all. And in the TT dirt, we have basically three densities. So we have the posterior itself, which is constant, because here I want to vary my threshold, my time. So the smaller is my threshold, the faster the particle must move, so the more difficult event I want to approximate. And maybe even we can start with the right picture here. So the probability of this particle escaping the domain. So the smaller I make my threshold, the lower is the probability. And potentially we can approximate the probabilities of like 10 to minus 18. So 10 to minus 10 is pretty much not a problem. But of course, we can also approximate not so rare events, if you like. And this is where we see the two other function approximations. So P gamma star is the optimal sigmoid instead of the exact indicator. And P star is using the actual indicator. So this brown curve here is the Hellinger error in the optimal Bayesian density, if you like. And if the event is not too rare, we can approximate it with like 0.3 Hellinger error, which is really nice. If you want to do MCMC on this, you get like 30% of rejections, which is really nice. Even for the most extreme cases, you'll get probably something like half of rejections if you want to run MCMC on top of this. But this is still, it's a very good proposal. I mean, and essentially you get dot correlation time of like 2 to 3. And it's a very good chain you can get out of this and approximate very rare events, really. So yeah, so to sum up, so basically if you want to get some takeoff message, the idea is if you can approximate a density function which you can integrate, then you can use just tempering or smoothing. So basically, if you want to approximate a multivariate probability distribution in UQ, in Bayesian inverse problems, in event estimation, anything like this, maybe even in generative models, as long as we have a formula for a normalized density and we can approximate the function in some integrable ansatz, then we can probably just use tempering to make a deep layer, to make a deep map, which is much easier to approximate. And also we can smoothen it. So if we have a function which converges to something discontinuous, maybe we can write a smoothing parameter which gives us the limit, the correct limit, but the intermediate layers will be easy to approximate. And basically the key ingredient is this map composition. So like we can use this simplified densities as generators to our map. Instead of training them from scratch in like neural network, we can use this more informative approach, especially if you do want to recover some multi-scale structure of our problem by revealing different temperatures. So TT is my favorite here because the TT cross is almost a direct method for the surplus maps. If you want to make these maps one by one, we have almost a direct method in TT. But potentially you can use anything. You can use polynomials if you like. Potentially you could use some sort of neural network if you can integrate it. So again, how exactly to compute the fast map without a tedious gradient descent training. Good question, but if you come up with an idea, maybe you can just plug and play it with tempered densities and it will be better than any normalizing flows or anything. Yeah, so to read ahead, so this QR code is given the paper of the rare events specifically, and if you play it with yourself, now we have a MATLAB code as well, and I think, well, yeah, we have a Python code as well nowadays, actually. I think we're still working on it, but if you want to try Python code, drop me an email, I can send you one, perhaps. And with that, I think I should conclude. Thank you for your attention. Thank you for coming. If you have any questions, I'm happy to answer.